Hello, and thank you for tuning into this session, Common Mistakes in Packet Analysis, Things that Make Traces Harder to Read. This session was delivered at Sharkfest 2014. This was the Wireshark Developer and User Conference that was held June 16th through 20th at the Dominican University, and we wanted to make sure that this was a session that was recorded and made available to those who wanted to see it. Just to introduce myself, my name is Chris Greer, work for a company called Packet Pioneer LLC, and at the company I am focused on network and application performance analysis. So getting in at the packet level, helping people resolve complex application performance problems, or helping them to root out root cause when things are going wrong. We provide protocol analysis consulting, and also when we're not out there actually troubleshooting problems, we like to bring that experience back to classrooms, share examples that we've seen out there in the real world, and helping people become better analysts. So also we deliver training that's focused on Wireshark, some other vendor supported products like Fluke Networks, and some others. So first of all, why do we care? What are we going to do in this session today? Well, when we're analyzing complex application performance problems, it's true that every packet counts. It's important that in order to truly find root cause of an application performance problem or some gritty issue that's been sticking around for far too long, it's important that we get a complete picture of what the problem really is. It's true that if we cannot see it, then we can't fix it. So here we see a missing puzzle piece. How frustrating that we come to the end of that puzzle and we find a piece of the puzzle is missing. And it's true sometimes that when we really get down to that packet level, sometimes troubleshooting and resolving a problem comes down to one packet. So we want to make sure that before we even begin that analysis and spend the time that it takes to read through a trace file, that we get everything that we're going to need and make sure that we're not making things harder on ourselves. Now, to put together this session for Sharkfest, one thing that I did is I interviewed a couple friends of mine that are consultants in the packet analysis world, and I got a list of things from them that they found that they repeatedly did, or when learning how to do packet analysis, mistakes that they made that made things harder on themselves. Things that they wish they'd done differently or known sooner so that all of this would have been a little easier. Now, why does this matter? Why is it important? Well, this screenshot might say it all to us. Sometimes this is what a packet trace can look like. It can look like a bunch of lines of code that can be difficult to see underneath. We can't, in some cases it can be difficult to turn the screen that we're seeing into actionable things that will resolve that root cause. So unless we really know what we're looking at and we're comfortable with those protocols, it can simply be difficult. Or it's possible that Wireshark could look to us like this cockpit does. Now, a trained pilot, he knows what he's looking at. He might take a picture like this. He might look at one of those dials and say, whoa, there's a problem here. Why? Because he knows what he's looking at. He's comfortable with interpreting what these tools are telling him, what these gadgets and dials are saying. Now for me, I'm scared if I look at that. I think I have an idea what the handlebars do, and I think I have an idea that you can pull them back and push forward, but the rest of that, it's completely foreign. And so it would make driving this plane for me, well, you definitely wouldn't want to put me in the driver's seat, but someone that's new to this, it's completely foreign. So in some ways, we can do the same thing with Wireshark inadvertently. We can make things more difficult on ourselves. I'm going to go through a list that I've compiled that I've found that are common things that can make trace file analysis more difficult. So the first one we're going to discuss today is initially capturing too much traffic. This screenshot was taken from the Wireshark University training, and it illustrates that we can put an analyzer at any point along the path that we're trying to get into. So say, for example, we have a client talking to a server. We have capture point number 1, 2, 3, 4, and 5. And those are just some examples of where we could possibly place an analyzer along the packet path. Now, if we place our analyzer close to the client, obviously we're just going to get the traffic that client is sending out on the wire. We're going to see what servers it's communicating with, what component of the whole application delivery is taking too long. That client, it's talking to a DNS server, it's talking to perhaps login servers or some type of Active Directory box, and then it's going on into the server that it's interested in talking to. So if we capture at the client end, we're going to see that detail, And we're not going to see the same type of traffic level that we would if we chose to instead capture on the server end. So if we capture on that server end, that's when we're going to see all traffic coming and going to that server. It is good that we'll see those dependencies. We'll see if that server is talking to any backend devices, any backend database servers, for example, or middle tier application servers. Now those trace files, when we do capture on the server end, those trace files can get large very quickly. And what that means, it gives us the type of feeling that we may be digging for a needle in the haystack. Now these trace files, how large would a trace file get if we're capturing on, let's say, for example, a 1 gigabit per second link? Well, let's crunch some numbers here. So if we take the file size that we would collect on a 1 gig link, and if we were capturing for 5 minutes, and that link averaged about 50% utilization, just looking at those numbers, how large would that trace file get? Are we sure that a problem that we're interested in would even happen within that span of time? Well, let's take a look. If we crunch some numbers, that would turn into about an 18 gigabyte file that we would need to comb through. That would represent approximately 300 million packets for us to comb through to find perhaps just one. Now, we just crunched those numbers based on about a 512 byte packet average. But that tells a story, doesn't it? In a 5-minute period of time, we're talking about 18 gigabytes. Now, I don't know about you, but that size of trace file, it's simply too large for me to wrap my head around. There's way too many conversations. It can take Wireshark a long time to open up those capture files. Now, in a lot of modern data centers, we can even multiply this by a factor of 10. Many data centers were pushing 10 gigs out to servers, right? So if we put an analyzer on a 10 gigabit per second link for 5 minutes, imagine it was going about 50% utilization, that file size is just going to go up by a factor of 10, right? We're going to get a 180 gigabyte file, approximately 3 billion packets. And it's possible that you and I are just looking for one. So let's do our best to not experience packet overload. Because even with filtering, locating the root cause of a problem can simply be overwhelming when we have too many packets. If it's available to you, if this option is something that you can do, then let's start at the client end. Let's make things easier on ourselves. Let's make filtering easier, and let's make finding that root cause from the client end easier on ourselves. Now, that said, it may be that we come into a situation where we're taking a look at traffic going to and from a server, and it appears like that server is taking too long to respond. Well then, that's when we want to move our analysis to the server end. We would want to take our capture equipment or whatever it may be, make sure we put it in the packet path over on the server end, and then we have more data that we can work with in looking for that application problem. Number 2, another important one, not thinking before capturing. What do we mean by this? Well, before we collect a single packet off the wire, there's a lot of information that we should collect to make that eventual analysis that we're going to do a lot easier on ourselves. We should think about what's our goal? What are we looking to achieve by capturing in this certain area? Also, what is quote unquote it that we're trying to capture? Sometimes we'll go out to a customer site and we'll sit down and talk about the issue that they're experiencing, and they use that word it a lot. They might say something like, yeah, it seems to happen every third Monday. It's a weird issue. It only affects Shirley and not John over there. Okay, so what is it? Explain to me the actual application issue that's happening. Can we get more specific? What application is it affecting? How many users are impacted? Does it change when I go to a different server or connect in from a different location? Those are a lot of things that are going to go a long way toward resolving the problem or helping us find the problem at the packet level if we do some homework in advance. Also, an important thing, where do the packets flow? We don't want to assume that packets flow through a certain link, and that's where we put our visibility tool. and then only to find out that we were wrong, that the traffic actually goes to a different server, or perhaps it's pathed around us on a different network connection. So where do those packets flow? That's also critical data that we need to be sure we know in advance. Also, capturing a problem doesn't necessarily mean that we can interpret what is actually happening at the packet level. So be sure to think before you capture. Don't just jump on a link, grab traffic, and then expect to be able to find that root cause before we take some leading questions that should get us there. A third point, capturing locally on a system. So in this example, let's say we wanted to capture traffic going to and from that client end of the connection. So we're over there on the left, we're on the client end, and we actually install Wireshark on that client, and we hit capture, and then we have that client generate whatever that problem was. Do our best to reproduce it. So this can cause some issues that, if we're not prepared to see them, can be difficult to interpret. Things like false alarms with TCP. Maybe we've seen this before. This happens because when we're capturing locally on our client, the Wireshark capture driver is attaching to that TCP/IP stack before some of those checksums are being calculated. So this is kind of an old way to save some time and save a processor hit, that as a packet, or a segment rather, was becoming a packet was being put into an Ethernet frame. What some stacks would do is that they would offload the checksum calculation of a packet down to the NIC card. So let me show you where that is actually in a trace file before going any further. So I'm going over to Wireshark here. And what I'm going to do, I'm just going to scroll up. I'm selecting any TCP frame. Now if I come down into my detail view and I go over to the transmission control protocol header, and if I come down to the checksum. So this checksum is something that when I'm capturing locally on a system, that checksum may not be calculated by the TCP stack. Instead, what it does is it leaves it uncalculated. It just puts a random number in there. It then sends that down to the NIC, and the NIC is configured to look for those checksums and correct them to fix those checksums before it sends them out on the wire. So when I capture traffic that's being sent out, a lot of times I'll capture it before that is sent, or rather before it's fixed. If I took the same analyzer and I put it outside the NIC card, then this checksum would be calculated. It would be resolved by that NIC card, and it would go out well. Now this is something that we can choose to disable within Wireshark. I'm going to show you how to do that briefly. If we come up to the TCP header, and if we right click, this is where we can get to our protocol preferences for TCP. Now here under protocol preferences for my Wireshark, I've decided to validate the TCP checksum if possible, or don't validate that checksum. So me personally, I choose not to validate that checksum. The reason why is because if I choose to validate it and I'm capturing locally on my system, I'm going to see a screen that looks like this. Wireshark is going to have all these problems, these flags, these TCP errors that come up in the packet trace, and they're flagging an event, a problem. Now to the untrained eye, this screenshot here, it's going to look bad, right? We're going to start looking at that sender and taking a look at what's going on the TCP stack. Maybe we'll replace the NIC card. We'll think, hey, there's a problem. This thing's sending out bad checksums. When in fact, this isn't a problem at all. It's a false alarm. It's not a real issue that's being sent out on the wire. So again, this is something we want to remember, that we may see TCP checksum incorrect for packets that our local system is transmitting. They are completely healthy and normal if they are captured from that station that's transmitting. If we see the TCP checksum is incorrect on any other transmitting station, so if I'm out there and I'm capturing on a wire and I see TCP checksum incorrect on a unicast conversation that I'm not a part of, well then that's something that I'd really want to look into and dig into. However, this is the type of thing that may trip us up if we're not aware that capturing locally on a machine, it may generate these types of issues. Also, we might see some weird things in our packet traces. And that's just a word I use because we might see things like 16,000 byte packets. Like if we go to the IP length field in our Wireshark, we'll actually see these large packets, and we may think, well, wait a second, how is it that my machine can be sending out 16,000 byte packets? Isn't it true it needs to chop them up into much smaller sizes? I mean, the largest frame size on an Ethernet 2 frame is 1518 bytes. That is if I'm not using a frame tag or some other type of header information. But about 1518 is about all that I'm able to send. So does that mean that I'm sending out overly large frames, illegally large frames? Well, no. If we captured these 16 byte packets, so to speak, outside on the wire, external to that local system, then we would see several small packets actually physically leaving the NIC. Again, we see this just before the stack segments them. Something else we may see, strange timing issues. It's possible that we could see in our delta time column, this is the amount of time between packets, or from the end of the previous packet to the end of the packet that the timer is set for. It's possible we could see all zeros. Now, we might be thinking that's impossible. It's impossible that I could see all zeros because no two packets can arrive at exactly the same time on one interface. There has to be some type of delta even on a very, very fast link. So it's possible that these were captured and the stack is simply not able to properly timestamp those packets. That's something else we might want to consider. Also with capturing locally, capturing on an end station, it's important to know that non-dedicated capture hardware has a limit. Now in this screenshot we see the fireman fire hosing packets at a laptop. Well, this is effectively what we do when we put a laptop in a situation where it doesn't have the capability of keeping up with the ingress traffic stream. Now how bad does this get? Well, let's think about this for a moment. Now, most Wireshark downloads, the recent numbers for the amount of downloads per month is in the order of 500,000 per month. It's according to the Wireshark Network Analysis Study Guide. Now, how many of those downloads do you think go directly to laptops? Of those users, how many of them leave the optimization settings at the default rate? Very likely most. So we find in most cases, Wireshark is installed on a laptop. Well, what's wrong with that? Well, laptops have a purpose. My machine, Dell, it was created from the Dell manufacturer, and they created this thing just so I can browse my email, or browse the web, do my email, work on a couple of applications, have a music player, play some movies, mostly to make me a happy user. Analyzing packets, capturing them off the wire is not the purpose of a laptop, right? So Dell is just it's gonna get some NIC manufacturer, it's gonna put that NIC card or that interface into, it's gonna attach it on the back of my machine, and I'm gonna plug in and I'm going to go ahead and start capturing packets. But my laptop is not an optimized hardware-based tool with the express purpose of capturing traffic and keeping up at 1 gig. Now, is 1 gig really capturing at 1 gig? If I connect my machine to the network, it likely has a 1 gig interface these days. But does that mean that my laptop can capture traffic at 1 gig speeds? Well, most of us would agree that our machines cannot keep up with a high rate of traffic. But the question then becomes, when does it start dropping packets? What is the percentage of traffic that I can be sure of that my machine can keep up with? Or alternatively, when should my eyebrow go up? At what point should I be concerned that my machine is not keeping up? Really, the question becomes, at what utilization point on a link do we really need to consider a hardware-based appliance that's purpose-built for doing packet capture and analysis? Well, I'm going to talk a moment about a demonstration I did. This is actually a year ago at Sharkfest 2013. If you're interested, you can find the video from that here on YouTube as well. But capture limitation on default settings. So what I did is I took a packet generation tool. You can see the Fluke Networks OptiView on the top left, and I pushed it through an aggregation switch. This was a 1 gig ag switch. I sent a traffic stream from that aggregation switch to my laptop. Okay, and what I did is I saw how much traffic I was actually able to bring in and capture off the wire. The results were pretty interesting. My Dell XPS 15Z, it's an i7, 8 gigs of RAM. It can consistently capture about an 80 megabit per second stream. Now that might sound alarming or surprising to you. It certainly did to me. If you think about it, what we're talking about is a very small amount of traffic, a very small percentage of traffic on a 1 gigabit per second stream. In fact, isn't that 0.8% we're talking about? And it's not much better on other streams. I'm sorry, 8%. And we find it's simply not much better on other streams. We find that systems simply aren't able to keep up with the ingress traffic stream. Last year at Sharkfest, we shot machines with static state drives, 16 gigs of RAM. We shot machines with Apples. We shot almost any brand you could think of, and very few of them were able to capture much over 100 megabits per second stream. So right there, my mental threshold when I'm capturing on a laptop, when I plug into a connection, if that connection's over 100 megabits per second or 10% of a gig stream, then my eyebrow goes up. I start to get concerned. I begin to question whether I'm effectively able to capture everything. Now, how do we know? How do we know if we're beginning to hit that threshold? If we plug in and capture on a stream, what symptoms should we look at in the trace file that will tell us whether we're not keeping up or not? Well, we want to look for expert information, things like previous segment lost. Now, it's possible that could be due to a true retransmission, but it's also possible that it could be that we simply did not see that original packet. Also, ACK lost packet when an acknowledgement comes across and we never saw the packet that this ACK is ACKing, right? It's acknowledging something that we didn't capture. And finally, it's possible sometimes this is also classified as out of order. It just depends on the situation. Now, something we also could keep our eye on is the dropped counter. On the bottom of Wireshark, we see there is a dropped packets counter. Now, this is something that, for me, in my professional opinion, I've also had to take with a grain of salt, simply because Wireshark is depending on the lower level NIC card settings or the counters that are on that NIC to be able to tell it whether traffic was dropped or not. So what I'll see on those tests that I was just showing you, when I shoot a gigabit of traffic at my machine and I'm dropping 90% of it, usually that drop counter is sitting at 0. So again, it's something that just because that drop counter says 0, it doesn't mean that we're effectively capturing everything. But it is a counter that we could keep our eye on. Switches and also virtualization can make capturing difficult. Now remember that when we're using a layer 2 Ethernet switch, a packet that comes into a port, it only will be forwarded to the destination port as long as that switch knows where that end station or the next hop along the station or along the path is. So in order to capture a packet, the analyzer needs to be in line somewhere. In our screenshot here, if that PC and that server are having a conversation through that switch, our analyzer, which is sitting out in space there, it could not just simply plug into a standard switch port and be able to see everything that we hope. Instead, we need to use one of the 3 common capture methods to get our analyzer in line. Now, these are familiar to a lot of us, right? We're familiar with the hubs, taps, and spans conversation. But what we're going to do here is we're going to talk about the pros and cons of each one. All of them have their plus and all of them have their minus. So getting in the path. A span mirror, what does that mean? Well, this will copy on selected ports, hosts, VLANs, or traffic patterns. It'll copy those things to a monitor port. Now there's some pros and cons. The positive aspect of a span mirror is a lot of switches already support it. We can log into the configuration and all we need to know is the commands to enable it, and there we are. It's free. It's there, it's built into the infrastructure, and we don't need to break a link to configure it. Also, it's full duplex traffic analysis. We can see traffic in both directions, and we can send that traffic over to our analyzer. Now, a span mirror needs configuration. That means we're going into a switch perhaps during a production time frame, dealing with production traffic, and we're going to make a change. In some environments, that's simply not tolerated. Also, our analyzer is not able to transmit back into the switch. It's also easy to overload if we're monitoring many ports. That means that we have more traffic being sent to the span than the span can effectively handle. All right, our next one, taps. Now a tap is something that physically goes in line on a connection. So here we see we actually physically break the connection between the server and the switch. We put the server on a network port on that tap, and then we have the tap going back into the switch. So it directly monitors the connection in line and lets us tap in or break that connection and listen in, sending those packets over to our analyzer. Now, just like with spans, these have some pros and cons. With taps, it's true inline analysis. We're not missing anything. It's full duplex. There's no configuration necessary. Most of them are power fault tolerant, so if the power gets pulled from the tap, the link doesn't drop. And it's also always there. It's always available for capturing. So in some instances, I found myself in a position where we put a tap in for an analysis job, and at the end of that job, the client may say, hey, you know what? Don't pull out that tap. Just leave it. We want the ability later to walk up, click in, and start capturing packets. Taps have a high cost compared to a hub and a span. And we also need to break the link the first time that it's installed, and they're harder to obtain. Now, over-provisioning doesn't only affect laptops. What we mean is that it's possible to send more traffic to a laptop than it's able to keep up with. The same is true with spans and mirrors. They too can be over-provisioned, especially when we're spanning a full VLAN or several gig ports at one time. And we did a test some years ago where we shot out a span versus a tap on one connection. Now you can find the details for this if you're interested in the gory details. I'm going to go over the highlights here, but you can also find this written up on lovemytool.com. So what we did is we took two stations and we transmitted a 1 gigabit stream between them. Now the PC on the right, we took a tap, tapping that connection, and sending that traffic over to a tap analyzer. Then on the span, we took that same traffic feed and we spanned that traffic over to a span port and sent it to yet another span analyzer. Now both of those analyzers were the Fluke Networks OptiView XG tool, so we were able to capture all traffic coming in from both the tap and the span. I was absolutely sure that the tool itself, or the analysis tool, was not responsible for dropping packets. What I wanted to see is, do both of these analyzers see identical traffic? Are the timers the same? Do they see the same amount of data? Well, let's find out what the basic results were. Tap versus span. So the tap capture results, the amount of packets that were captured on the tap, we saw 133,000 packets, more or less. And then, I'm sorry, not more or less, that's exactly what we saw. 133,126 packets. The delta time at the TCP setup, when we saw the handshake go back and forth between station A and station B, the delta time was 243 microseconds. Now, that might not seem like much, but we'll get back to that in a second. On the span, so the analyzer that was actually attached to that switch, the number of packets captured, we saw 125,000 packets. So right there, we lost 8,000 packets. The span was not able to keep up with the traffic stream. 8,000 were dropped. So right there, I have faulty information to dig through and analyze. It's going to be difficult to mentally jump my brain over those 8,000 packets. It's going to make the true problem look muddy, right? If we really did capture that true issue. But even more interesting for me was the delta time of the TCP connection setup, so 221 microseconds. If you notice, that's faster than the one on the tap. So when station A sent a SYN, I'm going to go back one slide. When station A sends the SYN, it goes through the tap, through the switch, and over to the station on the left. When the SYN ACK comes back from that station, it goes to the switch. The switch forwards the SYN ACK first to the span, and then after that it sends it to the tapped interface. So what we see here is that the switch was prioritizing ingress traffic over to the span. What that tells me is that was slowing down my true production traffic. Now, for me, that's a problem. When my analysis tool or my analysis method gets in the way of true production traffic, when it actually slows down the rest of the things that are going on in the network, and it causes them to suffer. So we never want our analysis tools or method to come at a cost of true performance on production traffic. Now, how do we get around this as far as an analyzer is concerned? These are boxes that are designed to capture at full line rate up to 10 gigabit per second and beyond. They stream to disk with no gaps or drops. One that we can look at is a TurboCap NIC from Riverbed. This is one that's going to be installed. It's hardware built into that NIC to be able to handle that ingress traffic stream. Also, the Cascade appliance from Riverbed. So the appliance, what it does is stream to disk, and it goes onto a connection, and it brings those packets in and writes them to disk as fast as they enter that interface. So we know between these two things that we're getting what we expect, and that our analyzer won't be muddying the waters, so to speak, when it comes to us reading the traffic. Okay, so now let's talk about the fifth one, forgetting capture filters. Now, to show this, I'm going to go back to Wireshark. Now, in Wireshark, when we're setting up a capture on an interface, one thing that we can do is come into our capture options, and if we choose to, we can set a capture filter. Maybe we've done this before, and we can set a host or an address here. Now, if I'm interested on a certain host IP, I can put that IP address here, and I can hit start, and I can set my capture filter so my analyzer will only bring in traffic to and from that machine. Now that's good, but what if I move this station from one connection to another and I forget that this is here, and I change my goal of analysis? Maybe I move on to a new problem. Well, we want to make sure that we go back into the capture options and we remove this, and that we don't forget that we have it set. Now, thankfully, if we're dealing with a recent version of Wireshark, if we shut down Wireshark and then bring Wireshark back up, those capture filters will automatically be cleared. But it's still something that we want to keep in mind if we're moving around to different connections. It's possible we could forget a capture filter. This is an interesting one, Wireshark Not Configured to You. Now, if we've had the opportunity to go to Sharkfest, we have a lot of great sessions on how to tune Wireshark to your visibility, your preferences, things that you are comfortable with reading. If we're using a Wireshark system that's been configured for somebody else, maybe they have too many custom columns. Maybe they have too few columns. Maybe they've configured some coloring rules that we simply don't understand. So what do we mean by this? Well, going back to Wireshark, I'm going to open up a simple trace file. Now here I have a profile that I like to use for when I demonstrate this. It's too many columns. So I'm going to come up here. It's going to resize that. So I have all kinds of stuff in my summary view up here. Now a column is something very easy that we can add to our summary view up here. If there's anything down here in the details that I want to see frequently displayed for every packet, well, I can come in, select that value, right click, and go to apply as column. it will then be displayed. That value will be displayed for all packets that have that header value, and it will be shown up here. But it's possible we just simply have too many of them to make sense of what we're seeing. A lot of times we want to start simple, and then depending on the application we may be looking at, or depending on the type of problem that we're looking for, we may adjust these columns, adding or deleting them based on our need. So don't have too many columns. Maybe this is a good amount of information for a certain protocol, but then say we're analyzing ARP traffic, a lot of these go away when we're looking at ARPs. It simply gets too messy, right? So something that we want to keep in mind, Wireshark not being configured to us. 7, taking the expert information as gospel. So when we go back into Wireshark, we can look at the expert system. Down here on the low left, we have a dot. If that's colored either red or yellow, that means that we have expert infos. We have warnings about this trace file that we might want to look at. So taking this as absolute fact, right? So it may be that we see things like on our slide deck information, we could see things like TCP checksum errors. So that's a false alarm when we're capturing locally on a machine. Or just last week I saw an example where we saw a TCP port that was being reused. Well, this isn't a problem as long as we don't have two TCP ports simultaneously being used by the same station. Now the server port doesn't usually matter, right? We're using the same server port all the time. But if two stations, if one station is reusing a port, that's okay as long as it shuts down one instance before it starts up the next instance. So in a trace file, there was nothing wrong with it reusing a port. It didn't halt the conversation. But in Wireshark, we did see that expert event. Hey, this station just reused a port. So it's something we want to consider, but in that case, there wasn't anything necessarily wrong. So we do want to make sure that when we see an expert info that we read it, we understand it, and we don't throw up all the flashing red lights on a problem if there really is none. And finally, number 8, the packet level distractions. This is when we allow packets that are not related to the root issue to distract our attention. So we could be looking at a certain application or conversation between a client and a server, and then we see IPX traffic coming off printers. And then we go down that tangent for a while and start to disable the IPX stack from old printers that we have hanging around. Or maybe we see some other type of spurious information, some spurious conversation going on, and instead of focusing on what we're there to capture and analyze, we allow these other distractors to take our attention. So let's focus, let's filter, and keep our interest where it needs to be to really get to the goal of what our analysis job is. I appreciate your attention to this video today. Again, this was Common Mistakes in Packet Collection. This was delivered at Sharkfest 2014. If you have any comments, please feel free to leave me one down in the comment window below. If not, then we look forward to seeing you hopefully at the next Sharkfest. Thanks again.